though non-determinism does not add power to finite automata in terms of language acceptance. Same language accepted by NFA and DFA. And that is, but obvious also we can convert NFA to DFA. We can convert any NFA to DFA. Example number 2. Converting NFA to DFA. And this is my NFA. We want to convert into DFA, deterministic finite automata. As per our textbook convention, we call it FA. When we say FA, by default it is deterministic finite automata. Fine. Now we can directly do it, or maybe we prefer table. It's preferred. If you look at, go back to the last example, just refresh. This was NFA, 0 plus 1 star, 1, bracket 0 plus 1, bracket 0 plus 1. That is L3. The third symbol from right is 1. The language is L3 as per our convention. Nth symbol from right is 1. Then the language we call it LN. And then this table, for this diagram, transition diagram, we have converted this into table. And then we have these columns in deterministic FA. One is subset S, then delta 1 S0, delta 1 S1. Subset construction algorithm. For every subset, there is a unique state in equivalent deterministic FA. And a rule of thumb is to copy the first row, Q0, the first row of NFA. This one we copied. And then subsequently for each subset, we define transitions. Subsequently for each subset, we define the transitions. And any subset containing accepting state of NFA, in our case it is Q3, becomes an accepting state in DFA. So that is 5, 6, 7, 8 contains Q3. 1, 2, 3, 4 does not contain, they do not contain Q3. So they are not accepting states. None of them is an accepting state. All of these 5, 6, 7, 8 contains Q3. So all of them are accepting states. My initial state is the first subset corresponding to Q0. So this is my equivalent DFA. This is sufficient itself. It conveys all necessary information. However, it becomes easier if we represent that using a state transition diagram. Visual effect of a diagram picture is always better than a table. So alternatively, we represent that using a diagram. Fine. From the examination perspective, not the internal exam, external exam, if such a thing is asked, draw this diagram also, because that external examiner might expect diagram. Otherwise, both of them convey equal information. Both of them convey equal information, nothing more in diagram compared to that of a table. Internal examination, either is fine. Fine. So we continue. Second example, NFA we know. So for our, because we will be applying that union, we'll be applying union. So it's easier if we represent the same diagram into a table, and that is my rightmost part, NFA. In your picture, the right part, Q, delta Q0, delta Q1. This is my NFA states. Q0, Q1, Q2, Q3, Q4. Here we have 4 states, Q0 till Q4. So those are states in the first column. Q is my state. And then we find out delta Q0 and delta Q1 from the diagram. Q0, on 0 and on 1. For example, Q0 on 0, there is a transition to Q4. And on 1, there is a transition to Q1, Q2 from Q0. On 0, Q4, on 1, either Q1 or Q2. And that is my row number 1. Q0, Q4, Q1, Q2. Similarly, for remaining states, we fill the table for NFA. Now convert this NFA into DFA. State transition table we have written. And now you apply subset construction algorithm. Very simple. Do it at your home. Okay, fill up this table. State Q or subset S, whatever you say. My first column, the leftmost part, equivalent DFA. Then we have delta 1 Q0, delta 1 Q1, or S, delta 1 S0, delta 1 S1, whatever name you prefer. So do that. Convert this into the NFA into equivalent deterministic finite automata. Is a rule of thumb, we copy the first row, Q0, Q4, Q1, Q2 from the rightmost table. That is for NFA. Q0, Q4, Q1, Q2. And we write in the form of subset. This is subset construction algorithm. For every subset, we have a new state. So my first row, that is Q0, second subset is Q4, third subset is Q1, Q2. So that is my first row. On 1, on from label number 1, state number 1, on 0, transition to state number 2. On 1, there is a transition to state number 3. So Roman 1, Roman 2, Roman 3 for 0 and 1 respectively. So that is my first row entries. Continue this way. You do it at your home. Work out this yourself. Very simple. Complete the remaining rows in the table. Compared to last example, this is a very small example. The last example, last subset, there were many entries, there were many states, there were many rows. Here, this is a fairly simple example. Just complete remaining entries. I'm waiting for you to complete remaining entries. Maybe in 5 minutes or so, complete this. Q0, Q4, Q1, Q2. So take next entry, subset number 2, and then fill it up. Label number 2, subset is Q4. Entries you need to fill up. Cells you need to fill up. Q4. In fact, this is simple. Q4, it is 5, 5. In NFA, the right side of your picture, you must have, you are doing it from this diagram. So Q4 on 0 and 1, Q4 on 0 and 1, right part of the table, it is 5, 5. So this is Q4, 5, 5. Please note that 5 is also a subset. 5 is also a subset. 5 is always a subset of every set. So for every subset, there is a new state. So we need to assign label to 5 also, to the subset 5 also. So Q4, 5, 5, labels, the label is 4. State number 2, on 0, transition to 4, on 1, transition to 4. Q4, 5, 5. So we have defined entries for number 2 state. Subset is Q4. Next we take up state number 3. The subset is Q1, Q2. The subset is Q1, Q2. So Q1, Q2 on 0 and 1. Look at the right hand side of the table for NFA. Q1, Q2 on 0 and 1. Very simple. It's union of those entries. Q1, Q2 on 0 and 1. Union of those entries. So it is 5, Q0, Q3. That is 5, Q0, Q3. Number 3, Q1, Q2. So we have to look into NFA table, Q1, Q2. Delta Q1, 0, union delta Q2, 0. So that is 5, union 5. Answer is 5. And delta Q1, 1, union delta Q2, 1. So that is Q0, union Q3. That is Q0, Q3. Again, Q0, Q3 a new subset. Yeah, very right. Cable, absolutely fine. Absolutely fine. Correct. Both the things are correct, Cable. So Q0, Q3 is level 5. Only thing is we have to define transition from every subset, from every set. We have to define transition from every state. For this subset 4, also there is a state, label 4. For the subset 5, the label is 4. And because every subset is mapped into a state, we need to define transition from 5 also. We need to define transition from 5 also. As it is a subset, it means it is a state. And in the case of DFA, we need to define transition from every state. So phi is also ultimately a state. That is phi. In fact, there is no transition from phi, so it is phi, phi, phi. It is phi, phi, phi. This normally we tend to miss such a row. This is DFA. A subset including phi becomes a state. And if it is a state, we need to define transition. So phi, phi, phi. So 4, 4, 4. Whenever phi is there in your entry, you can blindly put phi, phi, phi. You can blindly put phi, 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 but it is to be kept. It is to be kept. Next is phi, rightly said by Cable. Q0, Q3. Q0, Q3. Take out union. Q0, Q3 on 0 is Q4 and Q0. It is Q4 and Q0. So that becomes Q0, Q4. And then Q0, Q3 on 1, it is Q1, Q2 and phi. So answer is Q1, Q2, rightly calculated by Cable. Q0, Q4, that is a new subset, not existing previously, not encountered previously, therefore a new state. Label is 6. Q1, Q2 is existing with the label 3, so that is the 5th row. Q0, Q3 is Q0, Q4 is Q1, Q2 for 0 and 1 labels we have mentioned. So we have reached 5. Next it is 6, that is Q0, Q4. Yeah, Priyank very rightly said Q4 is 5, 5. 5, 5, 5. Very rightly said Priyank. 6 is Q0, Q4. Union is Q4, 4, 0. And Q1, Q2, 4, 1. And that becomes the entry. Q4 and Q1, Q2. Both of them are previously existing with labels 2 and 3 respectively. So those are our entries. And now we have defined transitions for all the reachable states from the initial state, which is 1. Which is 1. For these 5 states, number of subsets is 32. But out of that, the reachable states only 6. From Q0, remaining are 5. Total state 6. So only 6 rows we have defined. 2 raised to 5. Number of subsets possible is 32, but we don't need to define transitions for 32. We don't need to have 32 rows. Only we are considering reachable state from the initial state. So that is the reason we are following this sequence. That is the reason we are following this sequence instead of arbitrarily taking a subset. So that we only consider reachable states from the Q0 subset or the state number 1. So this is my equivalent DFA. Now we have to define initial state is 1, that we know. Initial state, that is 1. And accepting state is only Q4. So any subset having Q4, that becomes an accepting state. So 2 becomes accepting state and 6, 2 and 6. 2 and 6 are accepting states. 2 and 6 are accepting states. Subset containing Q4. Only accepting state is Q4. In the NFA, only accepting state is Q4. So any subset having Q4 and the state corresponding to that subset becomes accepting state. So number 2, label number 2 or label number Q4, whatever label you give, that is my accepting state. And then accepting state is label number Q0, Q4 or 6 as per your choice. So these are accepting states. Initial state is 1. Transitions we have defined. So that becomes my deterministic FA. I have not drawn that diagram. Table is sufficient here. I'm not drawing that diagram. Fine. So with that we complete. Second example for converting NFA to FA. Is that clear? Any doubt to anyone? Priyank, Keval, fine, Dev, fine. Abhi, Janil, Devans, okay, Devans, fine. Now we actually go back to our theorem. So we say we converted NFA to DFA. And we followed a typical procedure. Actually, that procedure for converting NFA to DFA, it is based on this theorem. To understand the theorem better, we went in the reverse order. This is the theorem actually. The claim is this. For any NFA M accepting language L, there is an FA M1 that also accepts L. This is the claim. This is theorem. This is theorem 4.1. Theorem number 4.1. See, let's see what is stated. For any NFA M equal to Q sigma Q0 A delta accepting language L, there is an NFA M. Those are the tuples. Accepted regular language is L. The claim is there is an FA M1 having parameters Q1, sigma, small q1, A1, delta 1 that also accepts L. So you can convert any NFA to FA. That is a claim, and that claim becomes truth if we prove this. In fact, the conversion from NFA to DFA, it is based on the concept that we are going to apply in the proof. For any NFA M, there exists equivalent FA such that language accepted is same for both the models of computation, for both the machines, M and M1. The model of computation is finite automata, the machines are M and M1. So if there is an FAM accepting language L, there is FAM1 that also accepts L. That's the statement. That's the reason if we can prove this theorem, that was the reason we claimed that non-determinism does not add power to finite automata, because any NFA is there, you can have equivalent DFA. So it's not the case that there is a regular language which can only be accepted by some NFA but not by any DFA. That is not the case. So model of computation finite automata, same power, whether it is deterministic or non-deterministic. Another model of computation, enhanced version of this, is called PDA, push down automata. And the third version, the most powerful, is Turing machine. So in finite automata and Turing machine, non-determinism does not add power. So whatever can be possible using non-deterministic model of computation, we can have deterministic machine accepting the same thing in the case of finite automata and Turing machines. In between there is push down automata. More powerful than FA, less powerful than Turing machine. So in that case, PDA, there is a difference. A non-deterministic PDA is more powerful than a deterministic PDA in terms of language acceptance. When we say power, it is always in terms of language acceptance. A non-deterministic PDA is more powerful than a deterministic PDA, which means now the class of the language that is accepted by PDA that you will study later, that is context-free language. There are some context-free languages which can only be accepted by non-deterministic PDA. Corresponding deterministic PDA does not exist. A non-deterministic PDA is more powerful than deterministic PDA. So these are three major models of computation. In first and third, finite automata, same power. Turing machine, the most powerful, same power, whether it is non-deterministic Turing machine or deterministic Turing machine. The second one, PDA, and NPD is more powerful than DPDA. That you'll study later. Fine. So with that observation, we return to our theorem. There is an FAM accepting language L. We can always have FAM1 that also accepts L. That is the claim. And here is a proposed construction. Let's, my Q1 is 2 raised to Q. And my small q1 is subset q0. I think now you can realize and now you can understand why we worked out those examples to understand this better. Q1, capital Q1 is what? The set of states in DFA. M1 is DFA, M is NFA. So which are the states in DFA? The states in DFA, based on our example, which are states in DFA? The states of DFA, anyone answer? Someone can answer this? Priyank, it is Q. It's not Q, but it's 2 raised to Q as such. The subsets. It is, yeah, it is 2 raised to Q, and that's the reason. Q1 equal to 2 raised to Q. All the subsets, they are states of DFA. Q1 equal to 2 raised to Q. Set of subsets. 2 raised to Q, that is power set. So all the subsets of NFA, those are states in DFA. Q1. Q1 means 1 when we say we are talking about DFA. Without subscript, it is NFA. So Q1, that is 2 raised to Q. Subsets of NFA. Q is a set of states of NFA. 2 raised to Q. From those states, whatever subsets we have, those are states in DFA. Q1 equal to 2 raised to Q. And that is exactly what we did in the example. For every subset, we have a state in DFA. For every subset, we have a state in DFA. So that is Q1 equal to 2 raised to Q, that we know. The initial state, blindly copy the first row. So my initial state is corresponding to the subset Q0. That we did. In both the examples, blindly copy row number 1. So my initial state, that is Q1, that is corresponding to the subset Q0. Q0 is initial state of NFA. So subset having initial state of NFA, that is the initial state of DFA. So Q1 equal to Q0, that we know. Now, next we define what should be A1, let's say. What should be A1? Can anyone mathematically define this A1? Accepting state in DFA A1. Q belongs to Urjit. Let me correct that as Q belongs to capital Q1. Partial answer is, instead of small one, it is Q belongs to capital Q1, Urjit. Basically, we are talking about capital Q1 is nothing but subsets. So Q belongs to capital Q1. Further, we have to put a constraint. Not only Q belongs to Q1, but with the constraint. Now Q1, what is Q1? Q1 contains subsets from the state of NFA. From the states of NFA, we have different subsets from, and Q1 is my set of subsets of NFA from the states of NFA. So Q belongs to capital Q1, and the further condition such that, now what we did there in accepting states, what we did in that subset, if there is an accepting element of NFA, in that subset, if there is an accepting state of NFA, then that subset becomes an accepting state in DFA. So it is Q belonging to capital Q1. We are taking one of the subsets, and the condition is that Q itself is a subset. Q intersection A is not equal to phi, rightly said Urjit. Q intersection A not equal to 5, absolutely correct. And just see this one, A1, my M1, that is DFA. So we need to define all 5 tuples of DFA. Q sigma, Q0, A1, delta 1, we need to define. Sigma does not change. Sigma does not change. So all the 5, Q sigma, Q1, A1, delta 1. We need to define this. We are constructing M1. So we have to define this Q1, sigma, Q1, A1, delta 1. We have defined capital Q1. Sigma remains same. Set of input alphabet does not change. Small q1 we have defined, and we were defining A1. So A1 is defined like this. Q belonging to capital Q1. Q1 already has a set of, Q1 is a set of subsets of NFA. So we are taking any such subset, and if Q intersection A, that is not equal to 5, then that becomes state corresponding to that subset becomes accepting element of A1. If a subset an accepting state, then that subset becomes accepting state in M1. This is my definition of A1. Rightly said, Urjit. Now, only parameter that needs to define is which parameter? Which is left to be defined, which is not yet defined? Transition function. Priyank, that is transition function of DFA. What is name? Delta 1. We need to define delta 1. How do we define that? Mathematically, how do we define that? What we did, we know in the examples. And those steps were based on this definition. So how do we define delta 1? We have to define a transition from a state in DFA. And a state in DFA, it is a subset. It is a subset of NFA. It is from subset of NFA. My set of subsets is Q1. Q1, capital Q1 equal to 2 raised to Q. So we take an element of Q1, that is a subset, that becomes a state in DFA. So we take small q belonging to capital Q1. So that small q becomes a state based on subset of NFA, subset from states of NFA. So q belonging to capital Q1, that will come, and we are defining a transition. Delta 1 is a state transition function. So we are defining a transition. So it is delta 1 small q comma A, where A belongs to sigma. We are defining a transition for a subset or state, whatever we say in DFA. So q belonging to capital Q1, delta 1 q comma A. So that is my q in, that is my state in DFA based on subset from states of NFA. So how do we define delta 1 QA, where small q belongs to capital Q1 and A belongs to sigma? How do we define that? So whatever procedure we have followed, we have to mathematically represent what we did. What we did. So for every element of that subset, suppose I want to define transition on 0. So we take every element of that subset and define transition on 0. For example, my subset is say Q1, Q2, Q3. For 0, I am defining transition. So what we did? Delta Priyank, delta star, not delta star, it is delta QA equal to Q1. Q1 belongs to capital Q and A belongs sigma. Can you refine this? What we did? It's not delta star. So what we did, again, I repeat, we take every element of that subset. We take every, and we were looking into the transition table of NFA. It means it is in terms of delta. As for our notation, the transition, I mean, my NFA is M, and M is having one of the tuples as delta. So what we did, suppose my subset is Q1, Q2, Q3. So what we did? For every Q1, that is element, for every state that is element of Q. Q is my subset. Already we have said Q is a subset. A belongs to sigma, Q belongs to capital Q1. So for every element of this subset, what we did? We looked at the transition function of NFA. So that is delta. Suppose my subset is, say, small q1, q2, q3. So on 0 we need to define. So what we did? We looked at q1 0, we looked at q2 0, we looked at q3 0. When we say it is q1 0, it means we are talking about delta q1 0, delta q2 0, delta q3 0, and then we took the union. So for every element of Q, so every R belonging to small q, Q is my subset such as Q1, Q2, Q3. We applied delta Q comma A and then took the union. Ultimately it becomes like this. For Q belonging to capital Q1, A belonging to sigma, delta 1, we are defining this for DFA. So delta 1 QA, like small q is the subset, Q belongs to capital Q1 and capital Q1 is a set of subsets. So for every R belonging to Q, so Q is my subset containing states such as Q1, Q2, Q3. So every R belonging to Q, so R will be Q1, then Q2, then Q3 in our example. And then we applied transition function of NFA. We looked into the table of NFA. We just recollect what we did. We were looking, say for Q1, Q2, Q3, we were looking at this table. We were looking at the transition of NFA. It means we were talking about delta. So it is union of, that is union of R belonging to Q. So every element of Q and then delta RA, delta Q1 0 union delta Q2 0 union delta Q3 0. If my Q is equal to, my small q equal to subset Q1, Q2, Q3. My small q, that is a subset having elements small q1, small q2, small q3. So we are looking at delta Q1 0 union delta Q2 0 union delta Q3 0, and it is delta because we are looking at the transition function of NFA, transition table of NFA. So that is my definition of delta 1. Is that clear? Is that clear? Is proposed definition for delta 1 clear? Priyank, Urjit, Keval. Okay. So that was the reason actually we worked out the examples. Otherwise, we have to start with this, and based on this definition, we calculate those examples. Fine. So this is my proposed M1. That is how M1 is constructed. This is my proposed construction. But then whatever we have proposed is to be correct and will accept language L that we need to prove. So the proof will follow. This is only my proposed construction. This is how I'm going to construct M1. Then I have to prove that my construction is correct. And here is just justification. The last definition of A1 is right because a string X should be accepted by M1. M1, when we say it is DFA. If starting in Q0, the set of states in which M might end up as a result of processing X contains at least one element of A. Because that is how a string is accepted by NFA. Multiple paths are there, and the end state after processing this X, in one of the end state, in one of the paths end state, there has to be an accepting state. So last definition is right one because the string X should be accepted by M1. If string starting in Q0, the set of states in which M might end up, here we are talking about M, NFA, as a result of processing X, contains at least one element of A. That is how a string is accepted in the case of NFA. Multiple paths are there. One of the paths at least has to end in an accepting state. So that is corresponding definition in DFA. multiple paths are there. Q intersection A should not be equal to phi. So this is why we have proposed that. Just small justification for that. Always whenever there is theorem, it is more challenging. So it is important to prove theorem. It is important to learn to prove a statement. So it's not just working out. We are not looking mathematically at this subject. We are learning how to prove a claim. That is more important. So this may not be you may not find it very easy, not find that much interesting, but it is very important. So we should focus on, whenever there is proof, we should not avoid them. We should learn them. We should not feel that we know the process of NFA to FA conversion. Actually, that is not just the purpose. Important things are these proofs. Whatever we claim, how we formally argue that we are learning from the subject. Fine. So the fact that M1 means DFA. The fact that M1 accepts the same language as M follows from the fact that for any X belonging to X star, the fact that M1 accepts the same language as M. M1 is DFA, M is NFA. It follows from the fact that for any X belonging to sigma star, delta 1 star Q1 X equal to delta star Q0 X. We are going to prove this. In order to prove that M1 accepts the same language as M, we'll be proving this closure delta 1 star Q1 X equals delta star Q0 X. Once we'll establish this, we'll complete our claim that language accepted by M1, that is L of M1, it is same as L of M. Language accepted by M1 is same as language accepted by M. In order to prove L of M1 equal to L of M, we are going to now prove delta 1 star Q1 X equal to delta star Q0 X using structural induction on X. We'll prove this statement using structural induction on X. Fine. So as we are going to use structural induction, we don't explicitly state integer n, but it is implicitly used, and implicitly it is length of X. So length of X equal to 0, that becomes my basis, and in the basis we want to prove delta 1 star Q1 X equal to delta 1 star Q0 X for X equal to null. So my left hand side is delta 1 star Q1 X is null, so that becomes delta 1 star Q1 null. And delta 1 star Q1 null is what? Ultimately, what we want to prove? Language accepted by M1, that is DFA. It is same as language accepted by M, that is NFA. So L of M1 is equal to L of M that we want to prove. For any NFA M, there is M1, and language accepted by M1, it is same as language accepted by M. That is the most important statement. In order to prove that, we have proposed construction for M1 from M. This is my proposed construction. Next, we'll prove that my proposed construction is correct. So in order to prove L of M1 equal to LM, based on this proposed construction of M1, we are going to prove, we will first prove delta 1 star Q1 X equal to delta star Q0 X. And once we prove this, we'll argue so that we can claim that L of M1 equal to L of M. So now we prove delta 1 star Q1 X equal to delta star Q0 X using structural induction on X based on the proposed definition of M1. So as it is structural induction, my initial value of n, we don't explicitly specify n, that is 0, means length of X equal to 0, it means X is null. So we will be proving delta 1 star Q1 null equal to delta star Q0 null. And here is my left hand side. X is null. Delta 1 star Q1 X is delta 1 star Q1 null. And what is delta 1 star Q1 null? Delta 1 means we are talking about M1. M1 means we are talking about DFA. So what is delta 1 star Q1 null in the definition of delta 1 star in DFA? Delta 1 star Q1 null is Q1. That is Priyank, correct. That is Q1. that is delta 1 star q1 null, that is equal to q1. And q1 is what? Now we go to our proposed definition. The initial q1, that is initial state of DFA. As per our proposed definition, it is set q0. q1 equal to set q0 by definition of q1. In set q0, can we relate this with delta star or delta 1 star somehow? Recursive definition of delta star, that is for NFA. If you recollect statement number 1, recursive definition of delta star for NFA, if you can recollect, we don't. Let me go back if I can show that for you. Rule number 1, recursive definition of delta star for NFA. Delta star q null is q, is set q. Delta star q null is set q. That is rule number 1. That is my terminating condition. Defining delta star for NFA, rule number 1, delta star q null is set q. And going back to our proof, what we had, we have set q0, so it is delta star q0 null. If it is q small q0, it means we are talking about NFA. And in NFA, the definition of delta star, rule number 1 is delta star q0 null is set q. It is curly bracket q. So it is delta star q0 null is curly bracket q0. That is by definition of delta star for NFA. And that is our right hand side. Null means x. That is our right hand side. Delta star q0 null, that is delta star q0 x. So we have proved the basis for this statement. Delta 1 star q1 x equal to delta star q0 x, structural induction proof. We are taking induction on length of x, that is our n. As it is structural induction proof, n is implicit. We no need to explicitly specify that, but the basis is length of x is 0. It means x is null. So we have proved delta 1 star q1 x equal to delta star q0 x for x equal to null. We have proved this. So we continue. We continue assumption for x is a string for which the statement is true. X is a string satisfying delta 1 star q1 x equal to delta star q0 x. Again, we don't say length of x is k, but in the next statement we'll take length of x to be k plus 1 implicitly. So induction hypothesis, this is a structural induction proof. The induction hypothesis is that x is a string satisfying delta 1 star q1 x equal to delta star q0 x. And next we take length 1 more than length of x, so that is k plus 1. So delta 1 star q1 xa equal to delta star q0 xa, that we have to prove. This is the induction statement. Hypothesis delta 1 star q1 x is delta star q0 x. Induction statement delta 1 star q1 xa equal to delta star q0 xa, that we need to prove. So delta 1 star q1 xa equal to delta star q0 xa. Now delta 1 star q1 xa, delta 1 star q1 xa is delta 1 star q1 x comma a, that is by definition of delta 1 star in the case of DFA. When we say delta 1 or delta 1 star, it means we are talking about M1. M1 is DFA. So we are taking left hand side, which is delta 1 star q1 xa, and that is the property of this closure. applied to delta star or delta 1 star here. In the case of DFA, delta 1 star Q1 XA is delta 1 star Q1 X A, and that is also obvious. That is there in the definition also. What is that? From Q1, after processing XA, tell me the state. That is meaning of delta 1 star Q1 XA. Starting from Q1 state, after processing XA, which state I can reach? That is meaning of delta 1 star Q1 XA. So what is that? Inner bracket, if I look at the inner bracket, so from Q1, find out a state that you can reach on X. That is delta 1 star Q1 X. That is a state. And from that particular state, on A, find out the next state. So there, once again, I am applying delta 1. When I say from a state for a symbol A, it means I am talking about delta 1. When I have multiple symbols, that is X, then I have to apply star. That becomes delta 1 star. So from Q1, for multiple symbols X, go to a state. And from that state, for a symbol A, find out the next state. So state symbol, it means outer side, it will be delta 1. You must have seen very in the previous part also, just a very simple explanation for that. So delta 1 star Q1 XA, it is delta 1 applied to a state for A, and that particular state is which? Delta 1 star Q1 X. So I split total, my input is XA, so I split into X and A. From the state Q1, I go to a state after processing X, and from that particular state, still I have to process A, I reach another state. So that is delta 1 star Q1 XA. That is definition of delta 1 star that we know. Fine. So we continue further. Already we have hypothesis where delta 1 star Q1 X equals delta star Q0 X. So far what we were talking, the previous expansion, it is everything is in terms of either delta 1 or delta 1 star. Ultimately, we have to prove delta 1 star equal to delta star. Delta 1 star Q1 XA equal to delta star Q0 XA. So delta 1 star equal to delta star. In this initial part, it is everything is in terms of delta 1 or delta 1 star. Now we introduce delta. So we use hypothesis. Delta 1 star Q1 X is delta star Q0 X. So we introduce here. Is delta 1, no change. Then delta 1 star Q1 X equals delta star Q0 X. That is my hypothesis. So I put there. It is delta star Q0 X, comma A by induction hypothesis. So it is delta 1, delta star Q0 X, comma A as per the hypothesis. Now delta 1 QA, delta 1 QA. Union of, by, let us look at our definition of delta 1. How we define delta 1? Delta 1 QA, our proposed definition, is union of R belonging to Q delta RA. That is our proposed definition. Delta 1 QA, that is union of R belonging to Q delta RA. Let's go back there. Delta 1, this is my Q. Delta 1 QA is union of R belonging to Q. Q is delta star Q0 comma X. Delta RA. That is our proposed definition. Delta 1 QA, the leftmost part. As per our proposed definition, that is our M1. In M1 we have defined delta 1 QA, union of R belonging to Q delta RA. So that definition we are using. It is based on our proposed definition. So delta 1 QA is union of R belonging to Q, and here Q is delta star Q0 comma X delta RA. That is our definition of delta 1. So my right hand side so far is union of R belonging to delta star Q0X delta RA. So we have already introduced delta in right hand side because ultimately we have to prove delta star Q1XA equal to delta star Q0XA. So right hand side we required delta, not delta 1. We started with the right hand side containing everything in terms of delta 1 or delta 1 star. Using hypothesis, we introduce this delta star. And then further, delta 1 QA, again using our proposed definition, we introduce one more delta or delta star. So now right hand side is in terms of delta or delta star. And what is this? Union of R belonging to delta star Q0X delta RA. Have you come across any such expression? Union of R belonging to delta star Q0X delta RA. Have you seen such an expression? Union of R belonging to delta star Q0X delta RA. Let me go back. Anyone want to reply this? Yeah, they rightly said second rule of recursive definition of delta star for NFA. Let me rule number 2, recursive definition of delta star for NFA. Delta star QIA is union of P belonging to delta star QY delta PA. Rule number 2, recursive definition of delta star for NFA. Delta star QYA is union of P belonging to delta star QY delta PA. Let's go back. Expression that we have arrived at. Union of R belonging to delta star Q0X delta RA. That is our rule number 2, rightly said by Dev. It is delta star Q0XA. That is delta star Q0XA by definition of delta star, rule number 2. Delta star Q0XA is union of R belonging to delta star Q0X delta RA. So this expression delta star Q0XA, it is nothing but our right hand side. That is our right hand side. This is our right hand side. So far we have proved delta 1 star Q1X equals delta star Q0X. That we have proved. Delta 1 star Q1X equals delta star Q0X we have proved. When we say Q1, it means we are talking about M1. M1 is DFA. Q0, that is NFA. That is part of NFA. So we have proved this. We have proved the expression. Now the last claim. That M and M1, they recognize the same language is now easy to see, easy to argue. M and M1 recognize the same language is easy to argue. Having proved delta star Q1XA equals to delta star Q0XA, after proving that, now it is easy to show that M and M1 accept the same language. Ultimately, what we have to show, language accepted by M1 is same as language accepted by M. L of M1 equals to L of M. That we have to prove. And that we can now argue, having proved delta 1 star Q1XA equals to delta star Q0XA. The M and M1 recognize the same language is now easy to see. How? A string X is accepted by M1. What is the condition for acceptance of a string by M1? Delta 1 star Q1X belongs to A1. M1 means DFA. Condition for acceptance of a string in DFA, that is what? Delta 1 star Q1X belongs to A1. After processing X, starting from Q1, processing starts from Q1, the initial state. After processing X, it has to reach to an accepting state. So delta 1 star Q1X belongs to A1. That is the condition for acceptance of a string in M1, that is DFA. Delta 1 star Q1X, that is a state because there is a unique path. And because we are talking about X, and not a symbol, not a single symbol. We are talking about multiple symbols. It is delta 1 star star. So delta 1 star Q1X belongs to A1. That is condition for acceptance of a string in DFA M1. Now we can now say that this is true if and only if delta star Q0X belongs to A1. Already we have proved delta 1 star Q1X equals to delta star Q0X, that we have proved the previous proof. So new statement, a string X is accepted by M1 if delta star Q0X belongs to A1. This is new statement that we have reached. And when this, what is something belongs to A1, what does that mean? Let us look at the definition. Something belongs to A1 as per the proposed construction. What does that mean? Something belongs to A1, it means something belongs to A1, it means Q intersection A is not equal to 5 for Q belonging to capital Q1. It belongs to N means that intersection A that is not equal to 5. That is how we have defined M1. So let's continue our argument. Something belongs to A1, it means that particular thing belongs to A1 means that state intersection A that is not equal to 5. So we conclude that this is true if and only if delta star Q0X intersection A that is not equal to 5. And what is meaning of this delta star Q0X intersection A that is not equal to 5? That is the condition of acceptance of a string by NFA. Delta star Q0X, that is my state, intersection A that is not equal to 5. It means that is the condition for acceptance of a string by NFA. In other words, X is accepted by M1 if and only if X is accepted by M. Therefore, L of M1 equals L of M. And that completes the proof. That completes the proof. So this was the last argument. Just proving delta 1 star equals to delta star, that is not sufficient. Using those equivalents, here we argue and show that the set L of M1 equals set L of M. The last part is also important. Just proving that delta 1 star Q1XA equals to delta star Q0XA, that is not sufficient. We have to prove, we have to argue so that we exactly show that L of M1, that particular set, equals the set L of M. Therefore, both the languages are same. That completes the proof. Is that clear? Is that fine? Let me get the feedback. Priyank, Keval, Dev, Abhi. Okay, so with that we complete this proof. Today's class, I'll share the notes also, and we'll continue from the new topic in the next lecture. We stop here.